So stationary point, turning point, and vertex all mean the same thing. That is, we can just call it the turning point. In a quadratic curve, this is the turning point. If we have maximum curve, this will be the turning point. Else, if we have a trinomial, there can be a maximum point and a minimum turning point too. So notice that, let's say for example, we have maximum curve and appreciate the fact that at the turning points the gradient is 0. Thus, du over dx is 0, and we will use this information to help us determine the x coordinate of the turning point. Once we have this, we will use the x coordinate and the equation of the line to find the y coordinate, and thus we have the coordinates of the turning point. Let's say, for example, we're asked to find the stationary point of this equation, this quadratic equation to be precise. So, we start off by finding du over dx. The differential is 6x minus 12. Since du over dx for a turning point is equals to 0, and we need to find the turning point, we will use this information and equate this to 0. I write this with red since this is important. This is the key point. And eventually, we will use this information to find the value of x, and x turns out to be 2. Since we are also given the equation of the original line, we will substitute the value of x into this line to find the y coordinate at x is equals to 2, and the y coordinate turns out to be minus 5. Thus, the coordinates of the stationary point, vertex, or turning point are 2, 5, 2, minus 5. Now, whether this is its maximum point or a minimum point, whether this is a maximum quadratic curve or a minimum quadratic curve, in order to determine this through differentiation, we find the differential of the differential, that is the double differential, and we double differentiate the equation of the curve and find d2y over dx square. This is the notation for the double differential, or you can write this as f dash dash x or y dash dash. Thus, in simple terms, in order to find the nature of the turning point, we need to find a differential of the differential. And if you get a finite value, it's going to be simple. Simply use these rules. Otherwise, you will have to substitute the value of x again, and I'll teach you how. So, if if the double differential is greater than 0, it's going to be a minimum point. If the double differential is negative, it's going to be a maximum point. Else, it's neither going to be a minimum and it's neither going to be a maximum. That is, in order to give you guys a visual representation, it's going to look something like this or like this. It, the gradient just becomes 0 for a small time. You guys need to understand that this is not a turning point. We call this a point of inflection, but you need not go into detail until and unless you are studying advanced mathematics such as A-level mathematics. You need not need this for advanced too. Just remember that it's neither a minimum nor a maximum point. And we'll cover the point of inflection in more detail if you are in A-levels in coming lectures. Oh, alright, so a few more examples. We start by finding the stationary point of this trinomial. So the differential looks something like 6x square minus 6x minus 12 is equals to 0. Since this is a turning point, this is a very important part. I'll highlight this too. Now, Taking 6 common to simplify the quadratic, this is what I have. And then x square minus 2x plus x minus 2, breaking the middle term, that is, I can solve this. I can make this into factors, and this is what I have. X minus 2 and x plus 1 turn out to be my factor. Thus, I have two values of x, that is, x is equals to minus 1 and x is equals to 2. Once you have the values of x, just imagine an imaginary separator here. I'll teach you why. Why I said imaginary? Because you don't exactly know. So, y is equals to 25. How did I get this? Because I substituted minus 1 back here. Uh, you should preferably show the working ladder. So, y minus, wait, I substituted y minus 1 here rather in the original equation. Always substitute in the original equation. Alright, minus 1 square and minus 1, and y turns out to be 25. I was correct. And in this case, we have a 2. So 2 cube minus 3, 2 square minus 12, 2 plus 18. And y turns out to be minus 2. Now you can make a separator till here. Now note that we still need to determine the nature of the curve. Sorry, should say the nature. So to determine the nature, we need to find a double differential. We will find a double differential of this, which turns out to be d2y dx square. This is the standard notation. 6x square has the differential of 12x, and minus 6x turns out to be minus 6. So this is the double differential, and this is why I said an imaginary line. So you continue working for both these coordinates separately. So this was a 2. Alright, so once I have this, again I'll do the working for this double differential. Copy, paste. Is equals to minus, no, is equals to 12 minus 1 minus 6 is equals to minus 18, which is less than 0. Thus, it's a maximum point. In this case, rather in this case, where x is 2, so it's gonna be a minimum point, since d2y over dx square is greater than 0. And finally, this is how you can leave your answer. Just a second. So we write this as minus 1 comma 25 is a maximum point, and we also have a minimum point, that is 2 comma minus 2. This is your answer. We'll bring this question down, and again we need to find the value, the coordinates of the turning point and the nature of the turning point. So first of all, do you have a dx? It turns out to be this, and remember that at the turning point dy by dx is 0. We start off by simplification, and we're left with this. We can break the middle term. Just note that we can break the middle term as minus 3x and minus x is equals to 0, and our factors turn out to be these. Just a second. So we have x minus 1 and x minus 3. Our x coordinates turn out to be 1 and x is equals to 3. Alright, so how did we get this? Because we equated the factors separately to 0. Alright, now how about we make a small line and then substitute the values of x in the original equation. We'll copy this down. Copy. So we have a 1 here, a 1 here, and a 1 here. So y turns out to be 2. In this case, we have a 3 wherever the x is. So the value of x is 3, and the value of y turns out to be minus 2. Yet again. So we have our coordinates 1 comma 2 and minus and 3 comma minus 2. We still are to determine their nature, however. So we need to find a double differential in order to determine the nature. That's the second part of the question. So this is our dy by dx. So we have a 6x and a minus 12. Not a finite value, so we need to substitute the values of x. We write this in between and continue the margin to avoid confusion with the vertex. Then how about we just copy this and substitute the values, or rather the respective values of x. So we have a 1 here and a 3 here, and thus this is what we have. In this case 6, in this case minus 6. This is less than 0, thus it's a maximum point. This is greater than 0, thus this is a minimum. We leave our final answer in this form. Just a second. So we have 1 comma 2. It is a maximum point. And 3 comma minus 2 is a minimum point. So this was our last example. And we learned how to find the turning points and their nature, and eventually how to lead the answer bit by bit. So this is the levels signing off.